Hello, community. So great that you are back. Today, we look at the latest model by NVIDIA, Reason 1. And you might say, why? Well, we have our LLM with a long chain of thought reasoning, and OpenAI 01 or 03. Then we have our vision language model with a long chain of thought reasoning. This is Gemini 2.0, where you upload an image and you can give here a verbal instruction what exactly to change in the image. And then we have our vision language action model. Like in my last video, I showed you here the beautiful Groot N1 by NVIDIA. But today we have something brand new, a physical AI for the first time, and it is called R1. No, it is called Reason 1. And it is called this for a particular reason. Let me explain. The main input is not anymore language. The main input is a video stream, a continuous sensor stream, video, audio, LiDAR, 3D, point cloud, whatever we have. Let's go in this video for simplicity with a video stream. Just want to make absolutely sure what we are looking at. This is what you will get. This is why NVIDIA developed Reason 1. We have as an input here a video sequence of 5 seconds. So you see here somebody pouring in here milk into a cup of coffee. And I have a question that goes with the video. And I ask, hey, the overall goal is the agent pours milk into the cup. The agent in the video is currently performing one subtask out of many to complete this instruction. For the agent in the video, what is the most plausible next immediate subtask? So I want to check if the system, the AI, understands what is happening in the video. Can I identify each and every object in the environment? What is the dynamic? What is the time development? What is going to happen next? What are the probabilities? And here on the right-hand side, you see now the result from Reason 1, the reasoning process. And R1 thinks, okay, let's see. The user wants to know the immediate next subtask after pouring milk into the coffee cup. The video has a coffee cup with a dark liquid, probably coffee, and the agent just poured milk into it. The action so far involved holding the milk bottle, tilting it to pour, and then stopping. Now, what's next? Well, after pouring milk, the usual step would be to put the milk bottle back. Since the milk bottle was in the right hand, the next logical step is to place it back on the countertop. The video shows a blue lid nearby, which might be the milk's cap. So the agent would probably close the milk bottle with the lid and set it down. Alternatively, maybe they need to stir the coffee with the spoon that's in the cup. But the question is about the immediate next action. Since the milk was just poured, the immediate next action is likely to stop pouring and put the bottle away. So placing the milk bottle back on the countertop makes sense. So you see, this is the internal reasoning process that we know from Deep R or from O3 or from O1 Pro. But now we only have as an input a video stream, and we have the internal knowledge of our LLM. But our LLM is special in this case. Let me explain. Here's a second example that NVIDIA gives us here, about the physical AI. So you have a video sequence here of a car driving along in this beautiful street. And now the question from a user, the query is, based on the vehicle's action in the video, what is the most likely immediate action it will take next? A, turn right, B, turn left, C, change to the right lane, D, change to the left lane. And now you can watch here the complete reasoning, the internal reasoning of Reason 1. Just give you here the option D, change to the left lane. And now the reasoning process, the AI tells us, hey, wait, but in a two-way street with double yellow lines, there's no left lane to change into. The driver is in their respective lane, so right for their direction, and the opposite lane is for the oncoming traffic. So changing to the left lane would be into oncoming traffic, which is dangerous and not allowed. So the option doesn't fit either. So after going through option A, B, C, D and nothing fits, the system comes now back and says, wait, maybe the question is a trick. The video shows that the road markings are double yellow lines, which means no passing. So changing the lanes is prohibited. Therefore, the driver cannot change the lanes. So options C and D are impossible. And now it depends. I can tell you here in Europe where I am, if we have a solid double yellow line, you are not allowed to cross this line. Now the reasoning of the AI, and I do not know if this is here the US particular traffic rule, because the system goes, so the only remaining option is turning right or left. So turning right would be here next street, okay? But turning left would mean crossing here over a solid double yellow line. And if the AI decides this is what it is allowed to do, you see, I hope this is not a mistake by the AI, but just a different rule set, because you are operating here on a different continent and I'm living on a different continent with different traffic rules. So you see that this is kind of interesting. And the video then, the analyst goes on and says, since the video does not show any turns and the driver is maintaining the path, maybe the answer is that none of the options are correct. So it is calculating the probabilities. And it says there are not any turns. There's no signal turn to the right or no careful, now you're allowed to turn or anything at all. So it calculates the probabilities and comes back with the final answer. I have no choice but to select none of the above. This is interesting if you only input this video. So what do we want? We want our next-gen AI to have a physical understanding of the world around us. This means the sensor provides all the information of the environment to our AI. The AI identifies all the objects, everything, the temperature, the pressure, the velocity, the speed, the impulse, makes all the calculation of the dynamics. AI predicts all next action probabilities, like I just have shown you in this idea of a car trying to understand what a double solid yellow line means. And AI understands the language and the physical world. So now moving, up until now we only had, if you want, large language model or vision language model, but now we want to extend the inherent understanding, not just of language and the reasoning, but also what do we see and what is this external world scenario capable of. So let's open up this video and let's have a little bit of fun with this new model. Now I wanted to have a look at the model, so I went to NVIDIA Cosmos Reason 1, Apache 2 license, said great, but it's not there, no? If you scroll down, the model family, coming soon, so okay. At the moment of recording this video, no luck. But in the video developer technical blog, we do have from March 18, 2025, some indication about the system. So let's go with this. And yes, I have a surprise for you. Spark. What is the spark of genius? So they say, yeah, we have a multimodal LLM. We want to focus on the visual world. We have a video input. And now we want to do all this beautiful long chain of thought thinking processes that we know from the language model. And now we want to do this here in everything. And this long chain of thought is also understanding not the physics of the external world. So what is the architecture of Reason 1? They now specify, and yeah, the surprise is that you can find here the real technical white paper by NVIDIA research with the official NVIDIA logo on this. And this is our source. I'll show you the paper in a second, but now we go a decoder-only multimodal LLM architecture where the input video is processed by a vision encoder, of course, what else? Followed by a projector, okay. And then we have a hybrid Mamba MLP transform architecture. Now this is nothing special, okay. But what's really interesting is and the data. They need to train this model, no? And they need training data. And now the main question is where they get the training data from. And you're not gonna believe it. NVIDIA, having all the possibilities and all the money in the world to buy any license from OpenAI, Anthropic, whatever, wherever you go, they go for DeepSeek R1 for the physical AI supervised fine-tuning data. So it is a simple model. Here you have the link now to the official publication by NVIDIA Research, the R1, the Reason 1 paper. What a coincidence that it is so close to the DeepSeek R1. You have two inputs. You have the video input and the text input, my question. Eh? So you have a vision encoder and a projector, and you generate the video tokens, and you have the human input text, and you have the text tokens. You've used them together, and you bring them here to your LLM, and you have a self-attention layer, you have your multi-layer perceptron layer, and you have a Mamba layer. And this is it. The output couldn't be simpler. Now, you might say, maybe the projector is some hyper-complicated, AI. I'm so sorry to disappoint you. It is a simple two-layer, multi-layer perceptron that aligns the vision embeddings into the text token embedding space. That's all there is. So you say, okay, what is now the core idea? Now, let's look at the technical deep dive. NVIDIA tells us we have now the intern vision transformers rendered me 2.5 as the vision encoder. And they have two models. They have a Reason 1 8B and a Reason 1 56 billion free trainable parameter model. And they say, for each input image, we adjust the image to a predefined aspect ratio segmented into 1 to 12 tiles, and each measuring 448 to 448 pixels. And this is here on GitHub, exactly the model that they use. It is free of charge, license MIT. Hugging Face also. And now you would say, but wait, we have also a 6 billion 448 pixel, no, in the version 2.5, yeah? This is also MIT and beautifully explained that it is available here on Hugging Face. Yeah, but NVIDIA decided, NVIDIA, no problem with infrastructure. They decided to go with the smallest 300 million model. Okay. So they continue. So for each video input, we sample up to 32 frames at a maximum rate of 2 frames per second. Everything goes back to 448 times 448. We have then the vision encoder generates 1K visual token, and we break it down to 256 tokens. Great. Now, here's a technical configuration for the Reason 1 8B and the 56B. You see the same vision encoder, just the projector has a different output dimension, because our backbone here, as you can see, is sometimes here the number of layers from 52 to 118, the model dimension from 4K to 8K, and the number of attention heads goes from 32 to 64. So those are the differences in the two models in the architecture. Now you might say, okay, this Mamba, is it somehow special that we go with the Mamba? And if you read the technical paper, you understand that the argumentation by NVIDIA is simply the quadratic complexity. But this is kind of an old argument, no, isn't it? Because if you just say, hey, I select now the state space models, the Mamba layers, there are 6 layers here, only for the long-range sequence modeling where we have a linear complexity, and I insert this now alternating with MLP. So I just have Mamba MLP, Mamba MLP. So this is how to optimize here the MLP understanding here in a linear complexity. But I have to go with the quadratic complexity of the transformer in each and every layer, more or less. This is an interesting choice here, but I will explain this in a minute. So what we have, this is the architecture here of the 8B model, and this here is the architecture of the 56B. And you see the only difference is here how often you repeat this layer structure 3 times compared to the bigger model 9 times. Okay. So we do have the transformer, the self-attention and everything with a transformer for understanding here the long-term relationship and the complexities of the deeper understanding. And we just do not go with an MLP here like in the classical sense, but we support it a little bit to help out with the linear complexity with a Mamba architecture. You remember yesterday when we talked here in detail about the architecture of N1 by NVIDIA, we had the same topic, you remember? I talked about the embodiment-specific state space, the state embedding space. And I told you, the simplest case NVIDIA does this here is the encoding via a multi-layer perceptron. And this now holds true, they just added here for the lowest complexity of a Mamba structure, of a Mamba layer. That is all there is to this idea. And I looked also back, you remember in June 2024, there was this beautiful paper of a Mamba 2 hybrid system. This was, I remember, done by NVIDIA, the University of Wisconsin-Madison, Princeton University, Together AI, Carnegie Mellon University, and Cartesia AI. And they developed almost a year ago this particular structure where they had Mamba and LMP layers mixed, And I think it is rather from a historical ground that they come up with this Mamba MLP structure. And I wonder how strong is the effect here of this learning here from a linear Mamba if you have your transformer complexity still into place. But anyway, However, if you just start out and you say, what the hell is a member? Well, you just go to my channel, you input here in the search member, and then you see here I have multiple videos on this member AI. The S6 is better than a transformer. The Jumper, a mixture of expert system. Then we do here the code, the fine-tuning, and the DPO alignment of a member system and an S6 system. I show you how to code member LLM for personalized medicine. And if you're a little bit interested in mathematics, I show you how we can go beyond the member AI, beyond an S6 structure, if we apply here some beautiful new idea for mathematics on vector fields. And you might say, hey, but vector fields was the topic in your last video on N1. Yes, exactly. Because I told you that we are operating in, NVIDIA is operating in N1 in 6 specific vector fields, in 6 specific embedding structures, with a different dimensioning and a different complexity. And now this would have been so beautiful to go beyond the member system into pure vector fields. But unfortunately, NVIDIA decided not to do this, not to build this next step model, but go with the old classic fashion member. Okay, I have to accept this. This was the main architecture. And I ask myself, so come on, so what is now special? Is NVIDIA only really doing chip design and system integration? Why is this model, this reasoning one model? What is it? Reading the paper, they focus on 2 topics. The common sense reasoning of a physical AI and the embodied reasoning. And I said, what is this? So let's start and have a look at the first one. This is the original literature by NVIDIA. So they tell us here, if we do an ontology of what we want to explore, we have 3 main elements, the space, the time, and the fundamental physics. And then we subdivide it into 16 fine-grained subcategories. And we want to generate here the understanding of the model. So what we do, we need to generate training data that focus on this particular aspects. Like in space, we want to have here a training data set that focuses here on relationship of objects in space. Or we want to have here training data that respects the causality in the time evolution of objects in a video frame. Or the camera angles in the time, or whatever. So also in fundamental physics, and I think this is interesting to me now, they say we want that the system has a training data set so that it understands mechanics, electromagnetism, thermodynamics, but not like I do, that I have access here, a function calling tool use, I have access here to a Python or a C++ coding. So where I can just say, okay, I do a numerical calculation, I kind of code a virtual experiment. We have all the mathematical formulas from Newton mechanics, electromagnetism, quantum electrodynamics, thermodynamics. And then we calculate numerically, in C++ here the data. No, they want to have just the fundamental physics. They want to have this in a classical AI training data set. So less enthusiastic, but nice that they have this idea. And they say, we believe that this ability in the common sense reasoning is essential for a physical AI. So everything is about a physical AI. So we move away from the language model, from the LLMs, the VLMs. Now physical AI is the next thing for NVIDIA. And if you think about this, we have now to do some fusion, because we do have the language description, we do have the internal thought processes, but now we have also provide here for the video understanding all the video sequences that go one-to-one with the language description. So you have now for each single sequence of chain of thoughts, you have to build here the video material that is exactly showing what your thinking or the AI system is thinking. Second part is about embodied reasoning. And you might say, what does it mean, embodied reasoning? The physical AI operates now in the real world. We have our little robot under the way, where environments are dynamic, uncertain, governed by complex physical interaction. Maybe it's raining, maybe it's dark, maybe it's not illuminated at all, maybe it's high temperature, whatever. So unlike the simple, basic, abstract reasoning, mathematics, programming, code generation, which manipulates simple symbols in a structured and deterministic manner, now we increase the complexity for the AI to understand this, no? Because now embodied reason requires the AI system to interact with and learn from the physical world. So we send it out in the real world, it interacts, it bumps into something, it looks at something, it tries to understand something, it moves in this environment, it tries to predict what it should do given the constraint of the physical environment and how to perform the task. So this embodied reasoning has a much higher level of complexity. Let's look at the ontology, like NVIDIA calls it. Beautiful, I call it. Just look at the 4 errors. 4 important things you have to remember: to process the complex sensory inputs, to predict the action effects, to respect the physical constraint. A car will not turn suddenly into a liquid. A car will not just fly away, or learn from the interactions. And I think this is the most important part. You want to have a self-learning system that the robot is really learning from its own interaction with a controlled environment, and more you accumulate knowledge. So, really an interesting paper. Everything is now grounded in real action by our AI system, enabling the robots not only to comprehend what they currently observe, but also to plan ahead their intelligent behavior for the future. And we will have here uncertain and a dynamic environment. Cars are passing by, people are maybe walking by, maybe it will rain in 2 minutes' time. You have a dynamic environment and you want your AI to plan intelligently. So let's come here to the facts. And we have here this beautiful technical paper by NVIDIA Research, Cosmos Reason 1, from physical common sense to embodied reasoning. And I tell you, here, beautiful, we have here our code pre-trained available under the NVIDIA license at this GitHub, but recording this video, it is still missing. Maybe you're lucky. Great. But let's look at the data generation and let's look at the training process. Because just because the architecture is a simple hybrid Mamba MLP transform architecture doesn't mean that the data generation, this is the most important part, and the training itself might not have some surprises for us. So, stage 1, easy. The pre-training phase. Vision pre-training, we align the vision and the language presentations. We have a data corpus of, NVIDIA has a data corpus of 130 million samples here, containing captioning and visual question answering data. Beautiful. Stage 2, supervised fine-tuning. Welcome, the classical one. We have 6 million image text and 2 million video text samples where we do the classical SFT. Stage 3, now this is new, this is special. Supervised fine-tuning, but now on the physical AI understanding. So we have our 2 categories of the physical common sense and the embodied reasoning. And we have special processing deadlines and data generation pipelines for this data. Remember, physical common sense, 16 subcategories, embodied reasoning, 4 reasoning capabilities, my 4 errors. Great. The data generation pipeline. Now I want to ask you, what do you think? NVIDIA, unlimited hardware resources. With what model did they went to generate data? Did they distill data, use the biggest OpenAI model? I mean, they have no problem to pay for the license to OpenAI. They went with a Google LLM or Anthropic or whatever you like. What do you think? If you have unlimited resources and no problem in hardware infrastructure, you say, okay, 10,000 GPUs, 20,000 GPUs. What was the model they went for the data generation pipeline? 3, 2, 1. DeepSeek R1. So for the question-answer pair generation, they use DeepSeek R1 generated reasoning, and for the reasoning extraction, they use DeepSeek R1 to provide the chain of thought reasoning annotation, focusing on the reasoning beyond the visual caption description. And we did some cleaning and everything. But I found it fascinating that NVIDIA and their latest model, the new model, Reasoning 1, they go and they rely on R1. Now we know why reason 1 and R1 are so phonetically close. And then we have embodied reasoning. And now again, the question to you. What do you think now is the best model? OpenAI? O1 Pro? The most expensive model in the world? Or what is it? 3, 2, 1. The reasoning traces for the embodied reasoning are generated, extracted, borrowed from DeepSeek R1, incorporating here the task goals and the current action states. So NVIDIA, having access to unlimited resources, each and every LLM on this planet, decided to go, I think, with the best one. Open source DeepSeek R1. I'm fascinated by this. Okay, this was the pre-training and we had our 2 supervised fine-tuning. And now I might say, hey, wait a minute, there's something missing, no? Your last 10 videos were on reinforcement learning, where is it? Ah, okay. Stage 4, physical AI reinforcement learning. And of course, we go here with a reward system, a reward function, a rule-based reward. And you might say, so what policy optimization do we use? And yes, it's not a surprise to you. NVIDIA went with a group-based reward policy optimization from DeepSeek R1 GRPO. So just to show you about the quality, what an open source model can have, the impact an open source model can have on the global AI infrastructure and AI development. So let's come to an end. Performance benchmark. Yes, we have in the NVIDIA research paper the performance benchmark. I just want to give it the result. All the further sub-details you find in the paper. So first, physical common sense benchmark. And we have here the benchmark selected by NVIDIA, particular for this NVIDIA model. So you know everything is absolutely perfect. And here we have it. Just look at OpenAI O1. We have a performance average of 59.9, so let's say 60. And then you see the very last line, Cosmos Reason, you have an 8B and a 56B. And the 8B has a 60.2, so let's say 60. So we have 60 compared to 60.2. And you say, wow. Now, please think about, this is a 56B model, so a small model. O1, I don't know the official size of O1, and it is not O1 Pro, so maybe O1 Pro is even better than the classical vanilla O1, but the latest NVIDIA Reason 156B comes close to OpenAI O1. Now there is one question nagging in the back of your head. You say, but wait a minute, there's something missing, no? Where are the DeepSeek R1 benchmark data? Because DeepSeek R1 was so essential to building and training here the Reason 1 by NVIDIA. So where are the DeepSeek data? Why are they missing in this chart? Nobody knows. The second test, embodied reasoning benchmark. And here we have all the tests selected by NVIDIA. Thank you, NVIDIA, for guiding us here. And then we have here the performance in the last line. You see again 63.7%. And now they are so much better than the vanilla OpenAI O1. And again, you have this. Why are the DeepSeek R1 benchmark data missing here? Unsolved mysteries, I can tell you. So, summary, here we go. NVIDIA tells us, our experiment showed that the physical AI supervised fine-tuning improves the backbone performance by 10%. And the physical AI reinforcement learning further boosts accuracy by 8%. Great data, great selected tests on benchmark by NVIDIA for the NVIDIA system, good. And then they do something where I think maybe the marketing department was a little bit involved, because they say, Reason 1 can now learn intuitive physics, such as the error of time and object permanence. Okay, so this is not physics. The error of time, yeah. Okay, so physical AI ontologies for physics, and they say, yeah, short summary, remember, 3 categories, space-time, fundamental physics, 16 subcategories, great. Embodied reasoning, remember my 4 errors, great. Have now predictive capability of the real-world interactions, hopefully. We have the elements, we know the architecture, we know the training data, we know the training processes. What is now the operational flow? It is easy. It is so simple. We have an input processing of the visual data, the video, and the textual prompts. We pass them through the visual encoder and the projector. We have a multimodal fusion. The visual tokens are integrated with the textual prompts and inserted into our backbone LLM that is simply here a Mamba MLP transformer architecture. We have a reasoning and a specific output. The output includes now the reason 1 reasoning process, the intermediate sort traces, and here natural language instruction for the immediate physical actions you could take. You remember the video, the very first beginning where I showed you the car driving here with some double solid yellow lines here on the street, or prediction of physical state and future scenarios. So you see where AI is moving to. Future prediction of physical state of the environment and how our AI system can interact or can solve a task in this dynamic physical environment states. Absolutely fascinating. And now NVIDIA tells us now AI integrates physics, well, part of physics, and understanding of the real world. Hello, marketing department, and you might say the WFM, you might say, and you say World Foundation Models. Ladies and gentlemen, I give you the World Foundation Models by NVIDIA. So you, if you go there, NVIDIA homepage, artificial intelligence, develop World Foundation Model to advance physical AI. Now I would say if the marketing department of NVIDIA tells us now that this are physical AI system, I would say, yes, okay. I'm so sorry I have to show you this homepage, but you get the idea. AI is developing, we are pushing ahead, we are moving ahead, we are now integrated here complete new complexities of the environment into the decision making. We are not stuck anymore with our language model that are just somewhere in the absolute vacuum of space, but we are now integrated in a dynamic environment. And I think it's absolutely fascinating what's going on. And you see the importance of one single open source model for all the models of the global leading corporation in AI development. So therefore, here you have it. This was a very short first look at the brand new AI system, the physical AI system, the latest by NVIDIA, Reason 1. And now we understand why Reason 1 has chosen this title here, because it is real close to R1 and Reasoning 1 and R1. What a coincidence. So, if you want to see more about this, hey, why not subscribe? And maybe I can surprise you in my next video.